yesterday.
It started.
Hello, Anthony and Izzy.
Hello. We miss you.
I like your boots.
Please come
Izzy.
back.
I like your boots.
Hamster's interesting.
And I like your shoes.
Your boots are somewhere in the house. So like
Where's
they're
one of
there.
your people?
Okay, our dot product. If we have a vector u and a vector v, then when we take the dot product, u dot v, the dot is not bolded because it's not a vector. We actually get a numeric value. We get a constant. Does anybody remember what we do with vector u and vector v?
What are we trying to do?
Matrices. I don't know.
We do multiply them in
Okay.
some way.
Wait, do you multiply their magnitude?
Sine and
No.
You just multiply them together.
yeah.
No.
Over what?
You take the product of the horizontal components plus the product of your vertical components.
When it's, I thought it's just another
We
like.
did that yesterday.
Yeah.
When did we ever multiply yesterday?
I'm pretty sure it was my homework.
You maybe multiplied a scalar.
Oh, this isn't scaling it.
Like yesterday you did 2 times vector u. And so you put 2 to the horizontal and 2 to the vertical.
I could have sworn we talked about this.
I'm pretty sure we did this in our homework.
Okay, open up your homework and show me the problem in which you did this.
Well, I didn't do it. I'm pretty sure I looked at the problem. It's like,
I'm pretty sure it's not until 11.3 that the book introduces the
I
dot
only
product.
added subtract.
I might have a relevant question.
Okay.
Okay, so we're doing dot products. Will we also be doing cross products?
At the end of second semester, yes. But we have to be in 3 dimensions for that.
Okay.
So, we won't do that until after we're done with all the AP stuff. But I'm gonna, at the end of second semester, we're gonna go through a bonus chapter where we come back to chapter 11 and we do everything in 3 dimensions. So we can do the cross product and do things with lines and planes and really cool things like that.
Could the
Okay.
bonus chapter be entirely bonus points? I'm just thinking that'd be good. Okay.
Not gonna happen. Okay. So let's talk about u
let's start with
dot v. It's going to be the same as,
V dot U.
yes, the dot product is commutative.
So is the U1 times V1 plus that, is that like another point again? Or is that just an add? Like,
I was going to wait to do an example. We'll just do one now. If you...
What?
No. I just, like, it'll be easier to just answer this with an example. If u is the vector 2, -1, and v is the vector 3, -2, then our dot product
6, 2.
is 2 times 3 plus -1 times -2.
Wait, if it's plus.
Why is it called a dot product?
Oh.
What does that mean?
See?
It means we are multiplying 2 vectors and getting a scalar.
so what does the scalar mean then? Why can't you get like another like vector that is the multiplying
So
product?
that is what we are going to do with a cross product, but we can't do that until we have 3 dimensions. We're going to stick to 2 dimensions right now.
So the product of 2 vectors is like a 3D vector? Is that what you're saying? Like,
When we take the cross product of 2 vectors, we get a perpendicular vector. Something that you do in physics with some right-hand rule, I think.
Yeah, magnetism. We'll do that second semester.
We will look at it also second semester. Caleb, did this answer your question for now?
Yeah,
You'll have another one for me later, right?
yeah.
Okay. I count on your questions. Keep asking them.
Not you, Richard.
Wow.
What, W?
It's actually double.
The dot product is distributive. I'm trying to bold my letters for you. Okay, since the dot product is multiplication, then we can view it as also being distributive because we know multiplication with numeric values is distributive. Okay. Also,
A quick question.
yes.
Would you say it would be easier to add them first and then do the
Yes.
dot product?
Yes, it would.
Okay.
Now, if you have a scalar multiplied to a dot product, technically we have two multiplications happening. If you have something like 2 times 3 times 4, okay, you do one product and then you use the leftover number for the other product. Okay, same thing here. We can do this product and then the scalar. We can do the scalar times u, then the dot product, or we can do the scalar times v, and then the dot product. But it's not a distributive thing because multiplication doesn't distribute to multiplication. Yes.
So, could you do the dot product and then multiply it by c scalar?
Yes, that is what is written first, right there.
Okay.
Okay.
I get it. Okay.
What is the dot product of a vector and the zero vector?
0.
Thank you.
Why do you say 0 vector?
So the zero vector is the vector where all components are zero.
Isn't that just a 0?
That's just nothing.
It's like an
But if we're in
imaginary
2 dimensions, it's the vector 0, 0.
But isn't that just
That's a dot, isn't it?
Now, V dot V is something special.
Yeah, it is.
You know what it is?
Yeah.
What?
V
I'm thinking it's 2b squared. I tried.
It is something squared.
Is it just
V squared?
2b squared.
That's what
The
Richard
dot
said.
product of V and V
That's what I said.
would be V1 times V1
Yeah.
plus V2 times V2.
V1 squared plus V2 squared.
Where do you find V1 squared plus V2 squared?
Oh, that's the distance formula.
The magnitude. It's under the square root of the magnitude.
But if they're the same, then it'd be 2b squared.
Then it would be magnitude squared because the radical's gone.
I like that. Also, I just want to say.
She looked
No!
directly at you.
I just wanted to say
I'm gonna throw up.
thanks for keeping this in 2 dimensions.
Okay, this is how we calculate. I couldn't help it. It got stuck. This is how we calculate the magnitude, yes?
Yes. Yeah.
Okay, so when we do the dot product, V1 times V1 is V squared, plus V2 times V2 is V2 squared. So it's just what's underneath right here is the dot product. So in order to get rid of this guy, we have to square it.
I like what you did there. That's a very steady finger eraser.
What?
You went on a really straight line. It was,
Oh.
it was kind of impressive, I'm going to be honest. They may not think so, but I do.
Okay, what can we do with the dot product? Because I know your question was earlier, like, what does it do for us? What does it mean?
Oh,
Okay.
turn vectors into scalars.
Okay, this is something that is based on the law of cosines. We're not doing the law of cosines. It's the formula just is derived from it. You don't need to know it, but the cosine of theta is the dot product over the product of the magnitudes.
It scares me that you almost said you don't need to know the law of cosine, but stopped yourself.
I have a hard time writing and talking at the same time,
Okay,
so
I
that's
was-
probably what happened.
Okay.
You don't need to know the law of cosines to be able to use this formula, but you need to know this formula.
I can at least.
You knew it once upon a time in pre-calculus.
Along cosines or this?
Technically both, but this is what I'm referring to.
There's so many bolts on my page, it's just kind of getting kind of crowded. It's just so much darker than literally every single other page in this.
Okay, what were the two vectors that we had earlier, Caleb?
I got it.
2, -1,
3, -2.
3. Yep.
But you totally just gave them to me in reverse order, didn't you?
Nope, that's what you gave us.
No, you was 2 -1?
Yeah.
Oh, okay. Okay, so if we want to find the angle in between these two vectors, then we're going to set up the cosine of theta equals, our dot product was 8, correct?
Yeah.
The magnitude of u would be radical 5. The magnitude of v is radical 13. So with your calculator in degree mode, because we're just going to take a break from radians this week, I would like you to calculate the angle in between these two vectors. Now, people, look up here. If you type in 8 divided by radical 5 times radical 13 with no parentheses whatsoever, it's not going to work. You have a product in your denominator. You need parentheses if you have a product in the denominator.
Or the little
Challenge
we need to be in
accepted.
pair with
It doesn't matter.
Radical 6.
Boom.
Correct.
No parentheses.
I have
Okay, well, it's the inverse cosine of
Oh,
that.
cool. I'm in degrees.
Inverse cosine of 8 over radical.
Wait,
Is it that?
is he gonna make?
What
is he
are
gonna-
you doing?
Is he gonna pose a problem that I'm still in that one?
Let's just get some.
Marina, what'd you get?
Why you say 60 there?
Oh, okay.
7.
I thought you were like
You're not there.
ready to go.
7.
7.125.
There's a problem.
One.
Use the inverse cosine.
Oh right, inverse cosine. I have to do that now.
Or
See, I rarely ever use the parentheses for dividing. I just go alpha y and do the
Make sure your degrees are right.
fraction thing.
Oh, you're
Oh,
right.
it switched.
Dummy.
it.
I like that much better.
Radians.
This is why I bring 2 separate calculators. One voice.
2, -1,
Stop.
3.
They're the same exact.
No.
Does it make sense that those are 7 degrees apart?
I would actually say yeah.
Perhaps.
Oh, hold on. I need to fix one of them, which stinks because.
7.125 degrees Fahrenheit Celsius.
There. I didn't draw the other one long enough. Okay, 7 degrees. My marker's pretty thick up there.
Fahrenheit Celsius.
Kelvin and
Degrees do that.
Please
It's like-
find me
Oh, that's true.
the dot
It's
product.
just K, right?
or
Sure.
I don't know. You could convert it though.
find me the dot product of
Why does it have to be 18? Like,
Oh.
It's
just find me the dot product.
it's times -1/6. It's just a -3. It's 0.
Spoilers.
Yeah, Jesus.
Is my
Yes.
brother in
Don't
this
yell things out.
Sorry. Got a little excited.
Chris really loves this.
What's our dot product?
yeah,
0.
0.
What does that mean?
That means
So
0.
I think what is 0?
they have the same
They're
angle from the
something
word,
way-
the x-axis.
That is a good
One of them,
idea.
no, it means one of you
They're
or
perpendicular.
me.
They're perpendicular.
There we go. We have
Discussing
orthogonal
zeros,
vectors,
90.
is what we call it in vector
What?
world. Okay? These two vectors are orthogonal.
What is it?
Orthogonal.
Like an ortho center.
Exactly.
What is it?
Because those are derived from right angles.
Okay,
I forgot that one.
218. That's not gonna be a good picture. Okay. When we have the cosine of theta is the dot product over their magnitudes.
Yeah.
Okay, well, really, I just have 0 on the right side, right? I'm not even gonna calculate those. What's the inverse cosine of 0?
1.
One.
90 degrees.
90 degrees.
The cosine of 90 degrees is 0.
Yeah.
So the inverse cosine of 0 is 90 degrees,
Pi over 2.
or pi over 2. Okay? So when our dot product is 0, we have perpendicular, also known as orthogonal vectors.
Wait a second.
Which means,
Wait.
isn't also one of them just be
3
0?
pi over 2.
Hold on, one person at a time. So we're always going to go with the quickest or the closest angle. 90 degrees is closer than 270 degrees. So our answer for angle in between is always going to be between 0 and 180 or 0 and pi. Because we're always going to go with the closest root. We're all about efficiency in here. Okay? All right, let's talk about some projection vectors. Let's really get into some physics.
Wait, did we finish that or no?
What does orthogonal mean?
Or are we trying to find
Perpendicular.
Perpendicular.
Why can't we just say
I mean,
Because
you can.
perpendicular? Why then?
So 90 degrees is the
Yes. Write it down. I'm not bullying everything. It's not going to happen. Otherwise, you won't be able to read my little w in my subscript. Projection. The projection of V onto W.
Whoa.
So the projection of V onto W.
How come when you do magnitude, it's not all of it?
Well,
Is it supposed to?
the inside of it would be.
Oh, it is supposed to be on the.
Yeah.
What does it exactly mean by projection?
What does that mean? Okay,
Being
so
laid
let's
on
say,
top of the other one?
kind of. Here is vector W. Here is vector V. We want to project vector V on to vector W. That's not that perfect. It's basically like we're shining a light over it, and it's like a shadow.
It's like finger puppets.
so it's not like if you like turned V so it was laying on top of it. It's literally just
It's like the
like
It's
the
the shadow.
horizontal part of it.
That's
like
kinda
I'm
what-
projecting like
that
the
seems
light.
kinda helpful.
So would
It's
the,
very helpful.
the hypotenuse is the same for V and the projected version? Like it's the same like,
Oh, you mean
Wait.
just
or is it
No.
more or less
Where's the
dependent?
where's the projection coming from?
So
90?
it's shining the light onto V, and it's the shadow that it casts on W.
So it's
So
not
would it
the
be?
same
It should be
length.
straight down from
Mhm.
terminal point.
So is this a vector or?
It's a vector. Because let's think about it. Dot product, number. Magnitude squared, number. So that's a scalar that we distribute into W. Okay? And
If it's on the.
as I hope that you have been catching on, If we have a vector and we multiply it by a scalar, then those two vectors are going in the same direction, or they're parallel, I should say, because they could be opposite direction. If we have a vector of any kind and we multiply it by a scalar of any kind,
It's still just one vector, right?
but the vector that we started with
Oh.
and the vector that we ended with are going in the same direction, which is this is a scalar multiplied to w, so this vector is going in the same direction as w.
Isn't it just longer?
In this case, this one's shorter. W is longer.
Yeah.
So we have to shorten the magnitude. Okay, so
Can't you just do Pythagorean?
Is the projection the same length as V?
Can't you just draw it down like
it is not the same length as v. It's like the shadow.
So
Yeah, it's
Oh.
can't you just drop down and then do that gives me down
I think he's trying to ask if it's the same length as.
Well,
the
but we're
horizontal
not-
element.
I mean, that's what this is doing for us.
but it's W is not always
Yeah, it's not going to be
always
horizontal.
horizontal.
Right. So this formula is doing that work for us. Okay.
So as Haley was saying, if it was like if they were perpendicular to one another, would there be no projection? Because the light is shining at the very top.
If they're
And what would our dot product be?
0.
Our dot product would be 0. So then we would have 0 times our vector. Yeah.
Why is
No,
there
I
no
think
light
it's-
on the very top?
In this specific case.
or they just
It's how I drew W.
Because W doesn't always have to be like.
It's
No, is that like
basically,
the general like.
it's kind of like the light is perpendicular to W. Okay? Yes.
So is the projection in this case like
straight up
just
in the
the
sky.
of V?
Where's the sun?
In my drawing, yes. But
Okay,
we're not
so
going to
you're
have
only-
horizontal W.
Yeah.
Okay? So, okay. Now, how do I want to do this? I'm trying to decide what to do first so you guys don't.
Alright, so this is the
Okay. The decomposition of V into V1 and V2, where V1 is parallel to W and V2 is perpendicular to W. Okay. We just talked about this.
Yeah.
If we have a vector and we multiply it to the scalar by a scalar, what is true about old vector and new vector? Okay. I'm going to be less general. They're parallel.
Is W a vector?
Usually the same direction, but if it's negative opposite direction, they're parallel. What?
Is W a vector?
Yes.
How is your component parallel to a vector? Yeah. How's that work?
This guy and this guy are parallel. Because if we put them next to each other, they're going in the same direction. Or opposite direction, but in this case, same
But does
direction.
the projected like vector have an x and y component if it's just 0?
Okay, so the way I drew this picture, W is horizontal.
It's not
But you're
always.
probably not going to have a
Oh.
horizontal W. Okay.
But if it was like that, would it be 0 then?
Vertical component, yes. So V1 is what is going to be our projection vector of V onto W. Okay. Now, let me get this picture drawn again here. Okay. If I want something that is perpendicular, how am I going to find that?
You gotta figure out what the dot product would be 0.
It's actually much more simple than that.
Oh, wow.
to be, believe it or not.
What
So
is
is it that projection of W on V?
Well, we're gonna use that.
Pythagorean theorem.
Gives you V2?
Is V1 and V2 still like the components, right?
No. V1.
V2 is a new vector.
So those are no longer like.
V1 is a projection
That's
vector.
when you subtract out the horizontal.
V1 is a projection vector.
So we're not.
V2
These
is
are
not
the same
component
V1
of
and
V2.
V2 that we used.
No.
No, let me bold this for you.
Okay, that makes more
Go
sense.
ahead.
That makes more sense. That's why I was. Okay. They're new vectors.
Okay, now, here is V. If I take V1 and make it opposite, those connect, right? So V minus V1. So if you take V and subtract out the projection vector, boom, we have the perpendicular vector. But I'm coming back to answer your question. Those would be the two components of V.
I thought they wouldn't be the same. Like it wouldn't be.
Well, no. I retract my statement. They look that way in this picture because W is horizontal. But it won't look like that if W is at an angle.
Yeah.
Do you see what I mean?
So they kind of are. The
They are in this picture.
But if W is not horizontal.
Then they're not.
Okay, that's fine.
Yes. We are on the same page, Richard. Okay. Let's calculate the projection of V on to W. So what do we do first?
Find the magnitude of V. No,
We want
wait,
the dot product.
the dot product.
So we have 2 times 1 plus 1 times 1.
Wow.
That's 2.
It's,
Okay.
you almost had it.
Then we need the magnitude of W squared
So first 2.
times vector W. So we have 3 halves I plus 3 halves J.
What did we accomplish here?
Got
That's the
That's
shadow.
that shadow. Mhm. Now, if I want the vertical, the perpendicular vector, then we're going to take vector V and subtract out the projection vector. So that vector would be
The perpendicular ones.
perpendicular to the projection.
Okay. Why do we need to know that?
Why is it?
Well, and probably a physics scenario, it could be.
So we're just learning how to do it, but no like actual application.
It's only 11:24.
Wow.
We have 10 and a half minutes.
So are we gonna learn something?
We're gonna do an example. I'm trying to decide if Richard has a question.
Yeah. Can you show me like an example of how I'm confused on how when you subtract the original vector and the other one, how that ends up being
So here's the projection vector,
Yeah.
and here's V.
Yeah.
If I flip this around and do the tail to head addition, we end up here.
She's making it negative. That's how she flips it around. She's adding it to V. is what
So
she's saying.
V
Yeah. So what you're saying.
minus the projection.
Oh. Okay.
Okay, excellent. We have a boat on a ramp.
Ooh.
A 600-pound boat, to be exact.
No way.
That's very specific.
On a 30-degree incline. Okay. What is the force required? To where my boat on wheels
Physics again.
isn't going to
Sailboat on wheels.
go into the water. Or street or whatever's happening. I don't know, maybe this is a driveway, maybe it's a boat ramp, I don't know. Doesn't matter. Okay?
Well, you
Just
were like
count
on a
static
water
friction.
slide.
Yeah. So friction.
And
For the mu. So
Wait, wouldn't there
coefficient
be
of friction.
kinetic friction too? Because you're moving it, like up
Okay.
the ramp.
So we have a
You think
force.
kinetic friction.
What? Wait, what?
We have a force of what?
600.
Times.
Times the acceleration of the Earth.
No, that'd be no. The force is 600
The force is 600.
Oh, yeah.
Mass gravity. Yeah.
So this vector I can write as negative 600J. Because it's 600 pounds down.
Not
We're doing vectors.
Joules is a capital.
This
J.
is bolded. Okay. Now, we need a vector V to keep it from rolling. Okay. Well, here, we have our boat ramp. We do need a vector to keep it from rolling, but let's talk about our boat ramp, right?
Basically disregard.
Disregard what?
Normal force.
Normal force.
I think you'll find this accounts for normal force.
Does it? That's what I'm asking. How does it account for normal force? Like if it, because we used to have to draw like normal force, like kinetic friction, and you had to
We
figure out
draw
this
Which
line
way would you draw normal force?
Perpendicular to the ramp.
perpendicular to the surface of the ramp.
So at whatever.
Like you
Like-
just draw it.
like
Yeah.
that?
Yeah.
Yeah.
Up this
Okay.
up the mast.
Okay. Give me a moment. Okay. So I'm going to make this vector V. Cosine of 30 degrees I and sine of 30 degrees J. Okay, so it's radical 3/2 I plus 1/2 J. Okay. And what we can do is we can take the projection of F onto V, and basically we get this right here so we know the force.
Wait, hold on. What are we doing in the red part that you just wrote down? I was still writing down the blue.
We're finding the projection of F onto V. I just want to know the amount of force needed. So we're going to take our boat weight and we're going to project it onto the ramp.
Wait, so couldn't you just find the force of V and then know that it would be the opposite of that? Or wait, no. would that
No,
be
because
wrong?
we have to account for the mass of our boat. Okay, so if we take the dot product of these two, what do we get? It's not a hard question.
Of what? F and V
Yeah.
would be I was.
How about 0,
-3.
negative 300? what is the magnitude of V?
That would be, oh, right.
Yeah, it's
3/4.
3.
So we have negative 300 times our vector radical 3/2 1/2. Okay? What's the magnitude of that vector? Hint. This had a magnitude of 1. Now, okay. So there's a force of 300 pounds that we would need to counteract that.
I don't know.
That's
So
also
this, I'm confused on how this is working. Is that accounting
Yeah,
for
like
the
what?
normal force?
The projection of F on V, like what
well,
vector is
considering
that?
that 300
And
is
the
less than 600,
friction.
yes, that is
Wouldn't you have
accounting
to
for the normal
overcome
force.
friction too? So it wouldn't even just be like the weight.
Wouldn't it be,
This is ignoring
so,
the friction coefficient.
it would be this one.
Oh,
Okay,
okay.
that's negative 300.
Mm-hmm.
This
Okay,
is
So it's
assuming,
like a frictionless.
Wait, it's with
uh,
yeah, it's
object.
assuming
tiny
it's an
black
ideal surface.
I don't know if it's drawn to scale, but yeah. The tiny black.
Oh, so this is showing us the force of the boat going down the ramp, and therefore.
So
we
that's
need
the force we need to
So
counteract.
therefore we need the
Yes.
Yep.
Yes.
So you don't
I
know.
feel like we did physics, but without having to account for the normal force.
Yeah, we just like skipped it, but
Yeah.
somehow we're.
Yeah. Okay.
Yeah, that's what vector
Now, what I do, I want to remind you of a type of problem. Like if you're pulling a wagon at an angle
Oh, yeah.
and I ask you for the work, we already know that work equals force times distance, right?
Yeah. But
Okay, but if I'm pulling a wagon at an angle and it's only moving horizontal, then what force do I care about?
The horizontal component.
The horizontal component, okay? So in this scenario, and I know we don't have time to do the whole problem, but we would have to take magnitude times cosine theta for our force,
Yeah.
because that's the only force that is acting upon the horizontal movement of my wagon.
Yeah.
Down to that.
Okay,
Projectile. It's coming back, Nate. It's coming back.
What is?
So
okay. Do you want me to try to throw up some numbers in the next 2 minutes?
no,
No,
I
you're
think
fine.
I think we're good on this one.
Okay, there is an example in your book that you can reference, and we have a review date tomorrow,
Okay.
where in past years, I've had to not have a review day. So,
What sense is the